We're going to focus on an instrument known as a mass spectrophotometer, the concept of isotopes. Now, this is all put together to determine the atomic mass of an element. In a spectrophotometer, there's a source, and the source will emit a beam of a neutral element, and we'll just call our neutral element X, in the gaseous state. As the beam of X, our neutral element in the gaseous state, leaves the source, it's exposed to a source of energy. The energy causes an electron to be ejected from the neutral atom, and it turns the neutral atom into a 1 plus ion. Before going forward with additional information on how the mass spectrophotometer works, let's revisit for a moment the concept of isotopes. Recall, an isotope is something where it's the same element because it has the same number of protons. However, in the nucleus, if we were to look in two different isotopes, we'll find that we have a different number of neutrons present in the nucleus of two separate isotopes. For example, we have the two isotopes, carbon-12 and carbon-14. Now recall the lower number here, the 6, that's the atomic number of an element, and that tells us how many protons are located in the nucleus of that particular element. Now the upper number, for example, for carbon-12, the number 12, that's the mass number. Now recall what that tells us is the sum total of the protons and the neutrons located in the nucleus. Now because the isotopes have the same number of protons, in this case 6 protons and 6 protons, but a different number of neutrons. In this case, we have 6 neutrons, whereas in carbon-14 there's 8 neutrons. The mass of the isotopes will be slightly different. The carbon-12 has a lesser mass, and the carbon-14, because of the 2 extra neutrons over what's located seen in the carbon-12, it has a larger mass. Back to our mass spectrophotometer. The beam of 1 plus ions of our isotopes is exposed to a magnet. Now the magnet, because the ions are charged objects, is going to cause the beam to curve. So there'll be some radius of curvature of our beam of the charged isotopes. If we look at a little bit of physics, the formula for centripetal force, F equals mv squared over r. So consequently, all these will experience the same force because the magnet's the same. An object that has a larger mass is going to have a larger curvature of radius than an object with a lesser mass. The radius at which it curves will be smaller. So to repeat, the X1 plus ions are exposed to a magnetic field. This causes the beam of charged ions to curve. Because the isotopes have different masses, the radius of curvature will be different for the different massed isotopes. Heavier masses have a larger radius of curvature. Lighter objects have a lesser radius of curvature. At the end of the beam, there's a detector, and this will count how many hits there are of each isotope. For example, as X1, the lightest mass isotope, hits the detector, we have 5, 6, 7, 8. And then another one hits for the middle mass, we have 2, 3, 4 hits. We have 5, 10, 11, 12, 13, 14, 15 as the isotopes hit the detector. This will give us a count of the relative abundance of each of the isotopes that occurs for this particular element. This data would say that the heavier isotope has the greatest abundance, the middle mass has the least abundance, and the lightest of the isotopes has a middle amount of abundance for this particular element. The results for a spectrophotometer are typically displayed as a bar graph. This bar graph, for example, indicates we have 9 hits of isotope 70, 6 hits of isotope 72, and 1 hit of isotope 74. The data from a mass spectrophotometer allows us to determine the isotopic abundance of elements. In this case, there's a total of 16 hits that struck the detector for the mass spectrophotometer. 9 out of the 16 came from isotope 70, so 9 divided by 16 gives us 56.25% isotope 70. 6 divided by 16, the total, gives us 37.5% is isotope 72, and 1 over 16 tells us that we have 6.25% of isotope 74 occurring in nature. Now, the data from a mass spectrophotometer is what's used to determine the atomic mass that we see on the periodic table for all of our elements. The atomic mass comes from, it's a weighted average of the masses of all the isotopes that occur for that particular element. To do a weighted average, what we'll do is we take the percentage in decimal form times the isotope mass, and then we total all these together to arrive at the atomic mass. So we have, in this case, 6.25%, we'd say it's 0.0625, times the isotope mass that we have, 74, for the one that had the 6.25%. We do likewise for our other two isotopes. Add these all together. When we add this up, that'll give us the atomic mass for this element. In this case, we end up with an average atomic mass of 71.0 for the data that we have in this particular mass spectrograph. One needs to be aware that sometimes the graph for a spectrophotometer will display the data with the percent abundance already determined, as we see in this graph for the element strontium. This graph indicates, for example, for strontium, the bar graph says we have 1% of isotope 84, 10% isotope 86, 7% isotope 87, and 82% isotope 88. This data could then be used, as we did previously, to establish the average atomic mass for the element strontium.